It's not the responsibility of the network team, even though that's the audience that I've designed the presentation for, nor is it the sole responsibility of the application team or the user interface team. Because a lot of the parameters, a lot of the tuning considerations interact, and tuning one section without understanding how that impacts the other might have a negative effect. So I'm going to start with just some old data that references the correlation between page load time, or speed, and business success, or revenue. Now that's something that we've done quite a few years in a row based on public websites, right? And a lot of companies have validated that data, and we all know that if we have an alternative choice, if we can go to a different website and get better performance, get better response time, we might make a decision to abandon a website that's running slowly. However, what about the applications that I'm using as a Dynatrace employee, right? I might use a travel application or a time and billing application. I don't have the choice of going somewhere else to enter my time unless I quit the company. I'm not going to do that. So we look at the benefits or the value of performance in a little bit different light, right? It's still very important, right? It's important to understand whether I'm satisfied. My productivity suffers. Maybe it's just not, it's not simply the matter of waiting for screens to update, but I'm going to actually give up and go do something else, go have a coffee or go take a walk, come back a little bit later, right? And the reputation of the IT department can suffer when performance is poor. So we are going to look at which web tuning practices that are applied in the public domain can be applied in a private environment, as well as which we can extend and actually gain more control over. And there are a couple of differences here I want to point out. Inside a corporate network, we likely know where our users are, right? We likely know what kind of network they connect with, right, to the branch offices. We have control over that, so we can design for those specific characteristics, whereas in a public website, we have no clue, so we have to design for everybody or for the worst case. A little bit about tuning disciplines. We separate backend tuning, which is database, compiler, memory, the business logic that runs systems, from the front end, which is really the connection between the client, the user, the browser, over the network and to the web farm or the web server. That's the front-end tuning. And a few years ago, a guy by the name of Steve Souders wrote a really good book. He's updated it a few times on web performance tuning, and he identified what he calls the performance golden rule, and that is 80% of the user's experience waiting for pages to load is spent on the front end. Right? So it should be clear that if we want to tune, if we want to improve performance of web applications, we should focus on that presentation tier, that front end tier. As a result of the emphasis on tuning and the importance of understanding that front end, there are quite a few tools. These are all free and very valuable. YSlow from Yahoo, PageSpeed is from Google. Those operate as browser plugins. Google also has a website, a web service that will do the same thing. Dynatrace still has a product we call Dynatrace Ajax Edition. That's been discontinued, but it also operates very similar to the other two, and it's still available, still works quite well. It's been superseded by the Dynatrace Atmon personal license, which is much more developer-oriented because it goes beyond the front end into some back-end code analysis. Those tools test the performance or the behavior or the characteristics of a web page against a series of best practices or against a series of characteristics, interactions, right? These are some of the more common ones. They test a few more than just these, but these are some of the more common ones. And they test for things like what's the size of your images or page components, how many page components do you have. They don't talk about the network. Some of the tools don't even reference the network. But the reason they're asking you about those, or the reason they're testing those, is because they care about the network. The reason they ask about image size isn't because they want to use tiny images. It's because if your users are connecting over a low-speed network, then large images are going to be a performance problem. Right? The reason they test for number of page components and redirects is because if users are connecting over a link with very high delay or high latency, then those large number of page components and redirects are going to affect performance. So they really are network-centric tests. They make an assumption, or a couple of assumptions, about the environment, that you have no control over the network, and therefore you must design for worst-case scenarios. Very low bandwidth, very high latency. Again, inside a corporate network, we know what the bandwidth values are. We know what latency is to our remote sites. And therefore, we don't have to design for worst case. We have to design for our users. Right? So that gives us some opportunities that are new in the corporate environment. So here's a little diagram that illustrates how complex corporate front-end networks might be. Right? Often much more complex than connecting through your home network to a public website. Corporate networks have load balancers and firewalls, but also application delivery controllers, perhaps WAN optimization controllers. The network team might have quality of service policies that they apply to prioritize certain traffic. So there are a lot of things that can be tuned to improve performance, but there are also a lot of things that can be mistuned to make performance quite poor. Right? Some of these devices operate at what I'll call the network layer. Right? They might intercept TCP traffic or affect TCP flow control parameters. Others operate at the application layer, where they might actually cache content for the user, or they might spoof application behavior to speed up application delivery. And one final point before while talking about applications, I think I'm breaking up here. While I'm talking about web applications specifically in this presentation, the guidelines, the theories, the parameters that we talk about apply to other types of applications that are not HTTP based as well. Okay, so now let me segue into a couple of TCP behaviors. Many of you, maybe all of you, have studied TCP theory. Some of you practice with it or make practical use of it. I did a lot of that as well, but I focus on just a couple of TCP behaviors that we care about from a performance perspective. These are the 5 behaviors. I'm not going to label them or name them, read them, but we were essentially opening up what we often refer to as the black box of the network to see how the network behaves, or to see more accurately how TCP flow control impacts data delivery. So the first simple is the TCP three-way handshake. Right? It's often referred to by the packet labels called SYN/SYN-ACK. It's used to establish a connection to a remote host. It also includes the receiver's advertised TCP window size, which is the buffer that the receiver has available to receive data as it's arriving. It also does 2 other things that we'll talk about in a few minutes. Resets the initial retransmission timer and resets the TCP congestion window. So there are a couple of performance penalties. So first let me illustrate or identify what that illustration is. I use that, it's actually a screenshot from a product, but I use that to illustrate timing, packet timings across the network. Each arrow represents a packet traversing the network. Red arrows are TCP acknowledgements or small packets. The blue arrows that you'll see later on represent data packets. Okay? So connection request, or setting up a connection, incurs what we call a round trip across the network. Whatever the latency is between the client and server, that's the cost of setting up a new TCP connection. In this example, that's about 700 milliseconds. So that's rather unusual. 700 milliseconds is an eternity waiting for a site. But I was in southern India, and the website was at our headquarters in Boston. So there was a delay across the network that was 700 milliseconds. There are two other factors, or two other things that happen that we care about in terms of performance when we open a new TCP connection. There's a parameter called the initial retransmission timer. That is set to 3 seconds by default. And there is a parameter called the congestion window, which is set to 2 packets by default. Next, we'll talk about the TCP receive window briefly. It's basically an advertisement or an indication to the sending node how much buffer space is available. In the past, up until a few years ago, the maximum receive window size was 65,535 bytes, right? I'm going to abbreviate that to 64K from now on, so I don't have to repeat that number. But that had been maximum receive buffer size until the TCP scaling option became available, which then allows these TCP buffers, these receive buffers, to become quite large, actually close to a gigabyte. High bandwidth, high latency links, which are increasingly common these days, right? Bandwidth is cheap. Globalization causes companies to own subsidiaries or partners around the globe. So I have high bandwidth, and I have people connecting over high latency links, and that allows, or that encourages or creates the possibility that a sending node will very quickly put a full buffer, a full receive buffer of data onto the network, and then have to wait for the data to be acknowledged. There's a bandwidth delay product formula. It's quite a simple formula, but it identifies how much data in bits or bytes can be traversing the network, actually on the network wire, crossing from the sender to the receiver. And here's a little table that lists or identifies, I'm not going to use the pointer, that identifies some bandwidth values across the top, some latency values, and it calculates on the bottom row the TCP receive window size that would be required for that TCP connection to saturate or use the entire available bandwidth. The ones that are highlighted in the light purple are TCP window sizes that exceed that 64K old earlier boundary, right? So those are the ones that would require the TCP window scaling option to be active if we want to avoid the TCP receive window performance constraint. So the question today is often asked, does window size still matter, right? We have window scaling. Virtually all modern TCP stacks support window scaling. Why do we worry about it anymore? And the answer is, especially in a corporate network, there are lots of things that will prevent window scaling. Often the servers themselves will disable window scaling to conserve resources. Devices, those devices I mentioned, the application delivery controllers, load balancers, and firewalls will often disable window scaling. So it is more common for window scaling to be disabled inside a corporate network than it is to be enabled. So the answer is yes, we still have to worry about TCP windowing. A couple of points. When we ask for a web page, we're actually making multiple requests for multiple page components. It's the page component size that matters, not the whole page size, because each component is downloaded separately. Little note, high bandwidth, high latency links, that's a mouthful. I can repeat it pretty quickly, but maybe not 10 times in a row. They're often called long fat networks, long meaning distance or latency, fat meaning high bandwidth, and they're abbreviated to LFN, which in English is the elephant. So if you ever hear an English speaker using slang and they call it an elephant, you'll know what it means. So here's an example and another diagram where the sending node on the right, the browser, transmit a file to the web server. But the web server has a quite common 32K receive window size set. Right? Most of the time, most of the traffic flows from the web server to the browser. In this application, there was a load that, that was taking a long time. So basically what's happening is the clusters of blue arrows that you see in the diagram represent a series of packets that carry 32,000 bytes of payload. Once the sending node has put that onto the network, it can't send anymore. It has to wait to make sure that the data has arrived reliably and has been acknowledged. So you see what happens on the sending side. It has to wait for the data to arrive at the receiving end, and then for the acknowledgments to come back before it slides that TCP window and allows the sender to transmit the next segment of the file. So in the illustration here, the problem we were trying to solve is why are we only using 20% of the available bandwidth when we want to upload this file to the web server? Okay, next we're going to talk about TCP slow start and its relationship to the congestion window that I referenced when we talked about the TCP connection setup. Right? When TCP opens a new connection, it has no concept of what that network might be. It might be a server in the next room on a local area network. It might be a satellite link with high loss and extremely high latency, and anywhere in between. So TCP, therefore, has to start up using a slow start, a very conservative slow start algorithm, so that it doesn't saturate, it doesn't cause havoc on the network. And it uses what's called a congestion window to manage that throughput. Now the congestion window is an internally maintained value. You don't see this in the field in the packets, but the sending node will use the default congestion window at the start of a new TCP connection, send 2 packets, wait for that data to be acknowledged, double the congestion window to 4, send those 4 packets and wait for those to be acknowledged, and then double it to 8 and so forth. So the illustration here on the right shows the ramp up through that congestion window where the first couple of blue arrows that you see right to left are 2 packets. That's the beginning of the congestion window. Wait for acknowledgements, double that to 4 and so forth until we ramp up. So each time we increase the congestion window, we incur that round trip link delay. Right? Again, high latency links make this problem pretty severe. Low latency links, this isn't a significant issue. So to get to that 64K window, I might need 8 round trips or so. My scaling goes beyond 64K, I'll need more round trips. And in the illustration here, the penalty to the user was a little over a second. Okay, 2 more theoretical sections and then a kind of a practical application summary. What happens when packets get lost? Well, there are 2 core effects of packet loss. The first will relate again to the congestion window. I mentioned the congestion window ramps up until one of 2 things happens. Either the receiver's advertised window size or buffer is reached, right? Maybe it's 64K. Once I reach that, I'm not going to try and send more data because the window won't allow me. Or the sender detects congestion. And congestion in large flows of packets is detected by what's called a triple duplicate ACK. So I won't go into detail on that, but it's basically 4 ACKs in a row, the single ACK and then 3 duplicates that inform the sender that we're still waiting for some data, and we're identifying that by the sequence number. When a packet is dropped in this scenario, it has the effect of reducing that congestion window by 50%. And then slow start is turned off and a more conservative congestion avoidance algorithm is used. So here's a graph of that behavior. The blue plot represents the number of packets in transit or on the network going from the sender to the receiver. So that's fundamentally the congestion window, the evidence of the congestion window on the network. And to point out, we're at packets here, and we reach about 30 packets at the peak of the blue. The brown plot is the cumulative number of lost packets and retransmissions. So what happens is we're increasing that congestion window, more and more data onto the network, trying to make better use of the bandwidth, and then we drop a couple of packets and we cut the congestion window by 50%. And then we ramp up again until we detect congestion again, and we drop down again. So this is often referred to as the oscillation in TCP behavior on a network. Engineers and scientists like to believe that this is in the practical world, it works quite well because we're sharing that network resource often with many other users. There's a second characteristic or a second way of detecting packet loss that is probably more applicable for our topic of HTTP applications or web applications, and this is the retransmission timer. Right? When a sending node transmits a packet, it associates that packet with a retransmission timer. If the data in that packet is not acknowledged before that timer expires, it's considered lost and the packet is retransmitted. Okay? So applications that are characterized by small requests and responses, right? How many packets is an HTTP GET request? It's 1 or maybe 2, right? Often the response from the server is 1 packet. So these are very small exchanges. We're never going to reach that condition of the triple duplicate ACK, which requires large flows of packets. The default initial retransmission timer, again, is 3 seconds. Now, as the connection is used, as data flows back and forth on the connection, TCP detects the characteristics of the network, and it will dynamically adjust that retransmission timer to something more appropriate to the link, usually quite a bit smaller than 3 seconds. But here's a click and wait example. So we've set up a new TCP connection. That's the SYN ACK or the 3-way handshake at the beginning. So we know new TCP connection. We send an HTTP GET request. It's dropped. What does the browser do? 3 seconds until the timer expires. It retransmits the packet, and then it doubles the timer to 6 seconds. Right? So this could get really bad if I drop the second packet as well. So the message here is that a single drop packet can have a dramatic effect on page performance, but more importantly, a drop packet early in the life of a TCP connection can have a devastating effect, where a drop packet later in the life of a TCP connection doesn't have that much of an impact. So there are 2 points here. One is, why do we wait 3 seconds to today's internet, right? If I'm a company entity in Poland and all of my users are at sites around the country, I probably don't have latency greater than 30 or 40 milliseconds to any of those sites. I should never wait 3 seconds to see if a packet is dropped. Yeah, so we'll talk more about how why we would adjust that a little later. There's another penalty there that's associated that I didn't diagram here. I'll diagram a little later, and that is the effect of the congestion window. Okay, so let's talk now about best practices. The first one is simple. Best practices when you're designing for limited bandwidth. So again, knowing your corporate network, you know how much bandwidth is available. If your link speeds are very high, you don't have to worry about best practices for limited bandwidth. You can skip it. Right? However, if you have low bandwidth connections, then pay attention to these best practices, and there's really just one. Keep this file size, the page size, as small as possible. Right? Cache content is probably the most effective way of doing it. Designing for high latency is more problematic, and we'll spend a little more time on this. Efficient page design here doesn't mean small components. It means fewer components, right? Because each page component requires a request to the web server and a response back. So for high latency links, that can be a pretty significant penalty. Minimize the number of TCP connections, right? Each TCP connection requires a round trip across the network as well. So persistent connections are pretty much universal if they're enabled, and we'll see an example in just a minute where they might not be. But keep those connections open so they can be reused inside the enterprise. Right? Limit authentication round trips. So we, within Dynatrace, used to use an authentication method that is referred to as NTLM. Right? It requires 3 or 4 round trips just to authenticate a TCP connection. So it's a very expensive, in terms of response time, authentication protocol. And then use browser cache efficiently. The conditional cache of if modified since. Why? Because if I use that, I still have to check the web server to see if the content I have is fresh. Right? Instead, a far future expires header makes more sense because I can simply look at the content in my cache. If it hasn't expired, I can display it without even contacting the server. So the chart on the right is a quick summary of some download consulting work we did at who was complaining about their time and billing application, and the baseline is the native response time. They had a Cisco WAN optimization solution in pilot. They turned that on and they gained a few seconds. They gained about a second of performance improvement, but that was a very expensive solution. And then we simply, in the third one, changed the caching approach from the conditional to the expires tag and had more significant performance improvement without spending any money. The third set of best practices extend beyond what those tools talk about and relate to TCP tuning. Right? So when we talk about tuning TCP flow control or TCP behavior in the enterprise, we can't simply think of the server and the client. We have to look at every one of the devices along the path, not the switches, but the other devices, the higher level devices along the path, because they may prevent the tuning efforts from taking effect. Reduce the TCP retransmission timer. Right? I worked at a global bank. We reduced the TCP retransmission timer from 3 seconds to 1.5 seconds. And while their users might not have jumped up and down saying, oh my gosh, this is much better, we know for a fact, based on traces, that we did improve performance in the case of dropped packets. That was a global network, had a fair amount of packet loss. Configure an aggressive slow start algorithm. This is relatively new in device configuration, but since bandwidths are generally higher these days, it makes little sense often to start with a congestion window of just 2 packets, especially if your latency is high. So many devices are offering the opportunity to increase the initial default congestion window. Right? I worked at one account, they had an initial congestion window of 16 packets. That was a little too aggressive because as they dumped 16 packets out on the networks, often half of those were dropped at the router, so they had to back off a little bit. Pay attention to TCP receive window sizes, especially if your application or applications are transferring large files. And then keep your TCP connection from timing out too fast, because if they time out too fast, not only do you have to reestablish a new TCP connection, but you start all over again with authentication and the congestion window and the retransmission timer. So here's a summary checklist where I've listed what I now call design inefficiencies. I think I used to call them, I won't say it, well, I'll say it, stupid developer tricks, right? Or things that you should never do. But there are real legitimate reasons for some of these. Sometimes you can't avoid them. So they're simply inefficiencies that, if they exist, will increase the application sensitivity to the parameters or the values on the right, on the top. Okay, one final example. This is near and dear to my heart because this was an internal application we were using in the US, and then we went to roll it out to our European subsidiaries or offices, and it failed miserably. But it wasn't my fault. So I'm just taking a piece of the web page. I don't remember the browser, so it's a mix of browsers, and all I need is one image, right? So I need an image. I play it. Here's what happened. Okay, let me open a new TCP connection. Make a round trip. I have to authenticate, right? We care about authentication, so I send this NTLM authentication message. That packet got dropped. The browser doesn't know that for 3 seconds. I retransmit that authenticate message. The server gets it, sends the check in response to that message. I get the challenge at the browser. The response to that challenge, the web server says, fine, I'll let you in. I issue the GET request for the file, and the web server says, oh, don't worry about it. The copy you have is okay. And to make matters worse, it then said, I'm not going to allow you to reuse this connection. You must close it. It forces a close. So I terminate the TCP connection, and for every one of those 15 or 20 images, I have to go through these steps over and over again. Now, not everyone had the packet loss in the same point, but many of the traces I looked at had 2 or 3 dropped packets. Every time we dropped a packet, because this was in the connection, it incurred 3 seconds of response time. So we went in the US from 5 or 6 second response time to roughly 35 or 40 second average response time in Europe, just because of some silly, they're not developer tricks, they're network tricks. Just the system was not tuned holistically to deliver that. And there's your result. Some gratuitous graphic that I just locally anyway. Okay, I'm going to end with a promotion. I practiced this earlier. Promotion has 2 definitions, right? One is I'm promoting my book. Yeah, that's kind of selfish. The second is it's a promotion to thank you for joining us, and that is we'll give it to you for what you want. Okay? So it's an expensive book, by the way, but it's worth every penny. It basically goes into these theoretical discussions and practical application of everything I've just covered here, but a handful of more behaviors. It's not limited to simply HTTP, a broader range of applications, and a handful of other application and TCP behaviors that are not quite as common as we saw here, but still exist and can still constrain performance. Okay. And I have a few minutes for questions, maybe answers if you ask the right question. Anybody have any questions? Yes. So the question was, do I think TCP is flawed, or do I think it's okay if we take care of tuning? And that's a great question, and the answer is yes to both. I mentioned that engineers think it's flawed, right? Because they're looking at the behavior, that oscillation behavior. They're looking at the algorithms to manage congestion, and they say that's terrible. It's so inefficient. And technically, it would be possible to improve performance, and there are different TCP stacks. You'll find them labeled things like Reno and Tahoe that experiment or implement different algorithms to recover faster. On the other hand, it works great for the purpose that it was built for, right? Do we care? Does anybody here care about TCP flow control when they're browsing the web? Not. It works fine. Sometimes it's a little slow, but it really works. It's a great protocol for what it does. It can be improved, and it's constantly being improved. But yes, it's both. Thank you.